My research involves designing, modeling, and fabricating advanced biochemical micro-nanosensors for environmental monitoring and sensing applications. Generally, biochemical sensors operate in two parts. First, the use of a recognition element that is sensitive to any interaction between the surface of the sensor and the toxin in question. Second, a specific transduction mechanism that generates a signal, which in turn correlates to the quantity of an analyte concentrant present on the sensor. The type of biochemical sensor I am designing and fabricating is an acoustic wave sensor. Acoustic wave devices are based on the use of elastic mechanical waves at frequencies well above audible range, traveling specially designed solid sensing structures. The detection mechanism is the acoustic wave, which propagates through or on the surface of the material. Any variations in the propagation path can affect the velocity and/or amplitude of the wave. These changes to the velocity can be measured by monitoring the frequency and phase characteristics of the sensor. The frequency characteristics of the sensor in turn correlate to the physical quantity being monitored. I am using a surface acoustic wave sensor because its waves, called Rayleigh waves, has wave propagation that's contained within one wavelength along the surface of the material. This in turn causes the wave to move very slowly within solids, yielding very high sensitivities among all the acoustic wave devices. The transduction mechanism I am focusing on to generate acoustic waves is piezoelectricity. Piezoelectricity refers to either the production of electrical charges within material by the application of a mechanical stress or strain, or use of an applied electric field, which in turn induces a mechanical stress or strain within the material. For a surface acoustic wave device to operate, an oscillating electric field is applied to create a mechanical wave, which then transverses through the substrate and then gets converted back to an electric field for measurement. To generate or excite the saw, I will need to apply voltage to finger-like metallic structures patterned onto the surface of the saw called interdigital transducers, or IDTs. When this saw is generated, I can determine resonant frequencies of the sensor and subsequent changes to these frequencies due to some type of a chemical mass loading on the sensor surface. For me to seek out the most optimal design of my sensor, I will need to incorporate numerous design and theory techniques, such as the type of piezoelectric materials to induce the acoustic wave, IDT and finger design, type of biological recognition element I'll be using, and understanding any interaction between the biological recognition element and the sensor operation. And that concludes briefly my project on SAW devices. Thank you.